All right. Hello, zoology people. Good to be back. Really excited about this next topic. We get into the class Chondrichthyes, which is a fancy way of saying sharks, stingrays, that kind of organism. So it's a lot of material. I'm going to try to break it up into multiple little smaller sort of discussions, lectures. But again, it's a neat topic to get into. I really like talking about this group. It took me a little while to put together the PowerPoint, but I think it's going to be concise enough. You can follow along within the book as well. It's not going to be sort of word for word, page for page, but the relevant information that's in the book, I think I'm going to summarize it as best I can and get to the point here in the lectures. So we begin with the class Chondrichthyes. Right, so Chondrichthyes is a funny sounding word. Chondro, referring to cartilage. And then ichthyes, CH is going to sound like a K in the Greek language. So ichthyes means fish. So this is a literal translation. If we magically went to Greece right now and you mentioned the word Chondrichthyes, you are actually speaking the Greek language, which means cartilage fish. It's going to be a little bit odd if you're just yelling that out in the street, but they'll know what you're talking about, right? So cartilaginous fish, which includes things like sharks, stingrays, and we're going to get into all those individual types. But first, sort of collectively for the entire class. So if you remember where we left off with the agnathan group, so agnathans, those jawless fish, the hagfish, the lampreys. So we said that there's some sort of transitional fossils between the agnathan group now into the Chondrichthyes group. Well, we start to see some of these shared characteristics, but a lot of new characteristics. Right? So this is sort of not completely unique to this group, but this is what they're most well known for. The idea of having an endoskeleton without bone. So we saw this with the agnathans. They're starting to have little sort of remnants of bone, but not quite yet. And same thing with these Chondrichthyes. They have multiple layers of cartilage, and it's actually quite strong, right? It's a dense tissue that serves them well for what they do, right? So these cartilaginous endoskeleton covered with these little scales that we're going to call placoid scales. And I'm going to show you a little microscopic view, but these are basically little precursors to like an exoskeleton, right? And it's going to have multiple purposes, but it's a characteristic of all of these Chondrichthyes groups. A tooth whorl, right? Tooth whorl. This is also characteristic of Chondrichthyes. It's going to vary from individual to individual, from species to species, but a tooth whorl represents an idea that these fish don't have necessarily a set number of teeth. Like you and I, humans, we have our baby teeth, and once we lose those, we have our adult teeth, and that's all we get. Right? So we basically have two sets of teeth through our entire lives. We don't have a tooth whorl. Cartilaginous fish do have tooth whorls. This is actually a fossilized remnant. If you look at maybe some fossilized pictures in the book, some representative species, these transitional fossorial species or fossilized species, they had these really sort of extravagant tooth whorls. Modern day Chondrichthyes have tooth whorls that look more like this. So basically, and we're going to get into that a little bit later as well. I'll show you some more details, but you have basically teeth that start out pointing back and that kind of move forward and move forward and move forward. So the newest teeth would be towards facing the back. The oldest teeth have moved out and are facing the outer side. So they kind of like a little transitional rotation that these things have. And they lose teeth often. If you imagine you're biting into bone, you're biting things that are struggling. So teeth break often, but that's okay because they're continually regenerated in these fish. This tooth whorl, that's what that represents, tooth whorl. And different for the different individuals, but the same concept applies. Again, a logical step in the evolutionary process is to move from the jawless agnathan group now to the jawed fish. So we're going to have well-developed jaws in all members of the Chondrichthyes. Males of all of this group will have basically like these paired claspers. A lot of people mistake these in males for the penis, the copulatory organ. Some people say, oh, that shark has 2 penises, right? That's not true. These are not actually penises. They are what we call claspers. They're going to be important in the reproductive process, but they themselves are not going to release the sperm, right? So we'll talk a little bit about shark reproduction later. And something else that goes back to the realm of physics, right? If you have a cartilage endoskeleton, cartilage is very dense. It's a very dense, heavy tissue compared to bone. So you have this thick, heavy, dense endoskeleton, which is going to make you very heavy. And in the water, in an oceanic situation, that's going to make this organism want to sink. So it would expend a lot of effort swimming and swimming and swimming, trying to maintain buoyancy. So to help compensate for that heavy, dense cartilage, we have a large liver that produces copious amounts of oil, this very lipid-rich type of oil. And this is where I wish I had you in face-to-face lab. We would actually dissect sharks and you'd get all slimy and greasy with all the oil of the sharks, right? So they are a very, very oily creature, but that's good because if you know something about, let's say, an oil spill, the oil doesn't sink. Oil is buoyant and it rises to the surface of the water. Basic chemistry, oil is non-polar, water is polar, so those don't mix. You can shake them, stir them, whatever. It doesn't mix. The oil will separate up to the top. So if you're a heavy fish filled with oil inside, it's going to make you more buoyant to kind of float a little bit easier. Right? So again, all of these characteristics apply to the entire class of Chondrichthyes. So everything that we're going to cover from here on out will have these characteristics. This is just sort of an X-ray of the endoskeleton. And again, that looks dense. That looks like bone. But again, it's not. It's cartilage, very dense layers, multiple layers of cartilage. So all that you see there is not ossified. There's no sort of calcium deposits in there. It's just strictly cartilage. So again, it serves them well. It's a way that they survive, and they've survived like this for many years. So it seems to be working for them quite well. So the cartilage endoskeleton. Here's a representation of the placoid scales. This sort of quote unquote like an exoskeleton, a remnant exoskeleton carried over from some extinct forms now into the modern extant sharks, right? And all Chondrichthyes. But on the sort of lateral view, a side view, would look something like that. From a top view, we see something like this. And this serves 2 purposes basically. It is a protective layer, right? It is going to protect, it's going to give some ossification, a hard surface. But also because of the way that they're positioned, it basically enables or enhances the shark's sort of hydrodynamic quality. So if you're going to be swimming through water, the more hydrodynamic you can be, the more efficient you can be, the less energy that you're going to expend swimming through there. So again, if you were to kind of put your hand at the front part of the shark and work your way across, it's smooth going this way. But if you were to rub it from back to front, it's like very rough and scratchy because of all of these little scales, these placoid scales that are pointing backwards. So again, protection and also the idea of being hydrodynamic, enhancing the hydrodynamic nature of the shark. So, and again, these are not to scale. When you catch a shark, if you look at a shark, you're not going to see them this size. They're almost to the microscopic sort of level, but you will feel them. Depending obviously on how big the shark is, those scales will be correspondingly large as well. But placoid scales, another characteristic of these cartilaginous fish. Okay, so again, even I, and I suspect you as well, we struggle trying to visualize geologic time, right? It's hard to envision this amount of time 390 million years ago. Right? Well, at that time, we call the early Devonian sort of period, the Earth was not as it is today. Right? So we didn't have these big land masses, North America and South America and Europe and Africa. It looked something like this. So you notice, man, there's a lot of ocean and a lot of open ocean. You don't have a Pacific and an Atlantic Ocean. It's just this vast area of water. And if you're an organism evolving in water, that gives you a tremendous amount of space, a lot of habitat. So just put yourself in that mindset. And this is where these organisms start to evolve and start to develop. So these, we're never going to get rid of these phylogenetic trees, but we look at that Devonian period. Right? There's our Devonian, also known as the Age of Fish. This is a time when we had a lot of fish diversification. We're going to talk about some of these names, the holocephali. We're going to look at the Galeomorphi, Neoselaci. These are all different types of names, Elasmobranchi. So just trying to introduce sort of the time scale. So early in the Cambrian, Ordovician, then we start to have this big radiation of species. Some of them still alive today. Some of these have gone extinct. But this is the sort of the geologic time scale, time history of these fish. So same idea, right? There's our Devonian radiation. We have a lot of diversity. And the ones that we're going to start to focus on, and I mispronounce these again, CH should be a K, the Neoselaci. Sometimes I say Neoselaci, Euselaci, but again, this is basically that node that gives rise to our modern sharks and stingrays. We have another node that branches off to some different types as well. So just, again, soak it all in. It's a lot of stuff, a lot of geologic time, millions of years ago, right, that we start to see these. And I guess the take-home message is that they've been around for a long time, right? A long, long, long time. And they really haven't changed too much, right? So I guess that saying goes, if it's not broken, don't fix it. They evolved to a certain point. The oceans have been relatively consistent. The oceans are still wet, still salty. So once they've evolved to that point, there's not a whole lot of reason to change at this point in time. So the idea of evolution in a geologic scale. So there's a lot of taxonomy as well with this group. And I'm going to try to tiptoe around all of the names. Some of them I'm going to have to address. Some of them I can skip around. But I'm not going to use the term class or order. Right now I'm just going to say groups. So the Chondrichthian groups. We're going to break this into two big groups, which you saw, the Elasmobranchii and the holocephali. So coming back here, the Elasmobranchii and the holocephali. So these are two very early separations in the history of sharks and cartilaginous fish here. So one of the first major sort of distinctions that happened goes back to that jaw formation, right? So we're in the process of developing a functional jaw, and the holocephali, which is actually considered more primitive, basically fused the jaw to their upper jaw. It's basically like a human system, right? So when we chew, our lower jaw, our mandible, is what moves. The upper jaw, the maxilla doesn't move, right? It stays in place. The elasmobranchi, they have two mobile jaw structures, right? There's two mobile jaw structures, and that are not, that top part is not fused to the maxilla on top, right? So we're gonna give that a unique name here. We're gonna call that a hyostylic, again, good test term here, hyostylic type of anatomy compared to the holostylic type of anatomy. So the arch, the hyoid arch is different. Hyoid arch is different, and the position, the flexibility, and the mobility is different in both of these jaws. So this holocephali group, holocephali was that first sort of fused jaw structure that happened. And then a little bit later in time, we start to see then this modification of this more mobile jaw. Now, if I give you the question here, well, what is the benefit of having this fixed jaw, or what is the benefit of having this sort of mobile jaw? So I'll let you ponder that. Maybe a good test question, we'll see. As we get into this hyostylic or hyostyly jaw action, the best example I can give you is that of the goblin shark. So I uploaded a link onto your Blackboard page, the hyostyly jaw action of the goblin shark. Right? All of that lineage, all of this elasmobranch lineage has this flexibility, right? It is not fused. However, the goblin shark it takes it to the most extreme. It's the most loose jaw, and it's the most rapid acting jaw as well. So very fast and an extreme amount of flexibility there. Again, the great white shark, the hammerhead shark, those also have the same type of jaw, but it's not quite as dramatic. But if you watch slow motion when they're attacking a seal or something, you will see that jaw kind of drop, unhinge, and can kind of extrude out of the mouth a little bit. So again, just showing you the functional jaw, not connected to that top maxillary type of bone. So that goblin shark. So check out the video that's on your Blackboard. Check out that link there. So again, just want to emphasize this major distinction, right? So we have the entire group, the Chondrichthyes, and then we have this branch that we call the holocephali, and then we have the majority of the other groups is the elasmobranchi. So elasmobranchi with that very flexible, loose jaw, the holocephali with that fused jaw. So again, it's going to have a big effect on their biology, depending on how flexible, how wide you can open your mouth. It's going to have an impact on what you can feed on. What you can feed on will have an impact on how you can grow, the size you can attain. So again, a lot of biology coming from that anatomy. So the anatomy allowing then for certain type of biology, ecology, and then continual evolution as well. So let me stop this one here for now. I'm going to stop it, and then I'll continue addressing each of these other categories as we go along, right? So it's a good stopping point for there. All right, so I'll see you very shortly again.